Hi everyone. Today we're going to talk about the last two topics of the course. One of those is the delta function, which is a way of looking at how to add an instantaneous impulse to a system, where impulse is a change in momentum. And the second thing we're going to look at is convolution and the role that it plays in the land of the Laplace transform. We've already seen it in the Fourier transform, where convolution in one domain turns into multiplication in the other, and a similar property is going to hold in the Laplace domain as well. To get started, let's actually talk about what impulse is. So impulse is change in momentum, or force applied over time. So the way that this typically gets measured is with an integral formula. So if you have a force function f of t that's changing as time goes on, so force is a function, then you could actually integrate from time 1 to time 2 the force function over time. And essentially what you're doing is you're adding up the effect of multiplying force by time. This is related to the way that work comes out of integrating force over distance. So this is called I. So this measures impulse. The way we've got this set up, we're going to just assume that f of t is equal to 0 outside of this integral. So if f of t is equal to 0 when t is not in the interval from t1 to t2, then we can actually rewrite this integral as the integral from minus infinity to infinity of f of t dt is equal to I. So it's going to be typical in the theory that we're using that we are going to assume that our functions are only active for some finite period of time, and then outside of that they turn into nothing. What we're interested in is looking at what happens to impulse as the time that the force is applied in goes to 0. So we're looking at instantaneous impulse. So we want to model instantaneous impulse. And if you want a picture of what instantaneous impulse looks like, an instantaneous impulse is like a strike, a punch, a hit, a shock. So instantaneous impulse changes the system instantaneously, as opposed to an impulse over time, which is usually thought of as a push, versus impulse over time, which we think of as a push instead. Okay, so we want to model strikes. Now, in the context of the differential equations that we've been studying, how would that apply? Well, when you flip the switch on a circuit and current starts flowing in, that happens instantaneously, or at least in theory that happens instantaneously. Or if you have a spring system that's oscillating and you strike the system with an object, that's an instantaneous change in the state of the system. And those are the sort of forces that we want to be able to understand in the context of modeling in differential equations. To study this, we're actually going to need to define a function that is going to give us what's called a unit impulse. So we want to study a family of functions that give us a unit impulse. That is, the impulse is 1. Okay? And we also want that to be instantaneous. So we want to study a function that has two properties. One, the force is instantaneous. And two, the impulse is unit. And anytime a mathematician says unit, you just mean equals 1. Okay. So to define the family of functions that we're going to use to study this, we're going to use the unit step functions from the previous chapter. So let's define a function as follows. We're going to call the function delta epsilon of t minus a to be equal to ua of t minus u of a plus epsilon of t divided by epsilon, which is really secretly just 1 over epsilon times ua of t minus u a plus epsilon of t. And it's easy to see what's going on here if we make a graph of it. So what is delta? Delta, because it's built out of step functions, is 0 until you get to a. And then it jumps up to be 1 over epsilon for a while. So it pops up and it's 1 over epsilon for a while. But then as soon as it gets to a plus epsilon, it falls back down again. And then it's 0 forever. That's the effect of this switch here. The UA turns on at a, and the UA plus epsilon turns on at a plus epsilon, which turns the whole switch off, because then you have 1 minus 1. What is the area of this function, underneath this function? Well, it's 1, because this rectangle is epsilon wide, and it's 1 over epsilon tall, and 1 over epsilon times epsilon is 1. So the impulse in here, I, which is the integral of delta a plus epsilon of t dt, is 1, because the area under the rectangle is 1. So this is a family of functions who all have unit impulse. So now how can I take the family of functions I just built and look at what happens instantaneously? So you should be suspicious here, because if you're careful, you'll see that I've set this up as a derivative, right? This is a derivative type structure. So I should be able to somehow take a limit of this thing, and it's a difference quotient. So the fact that this difference quotient is going to exist is going to be due to L'Hopital's rule, say. But really secretly what we're going to do is we're going to integrate this derivative, and then some function is going to fall out, except it's not even going to be a function. But this family of functions was chosen carefully so that this is a difference quotient. And when you integrate a difference quotient, you get an object back out. That's the fundamental theorem of calculus. So how can we study instantaneous impulse? Well, the first idea you might have is, let's take a limit as epsilon goes to 0 from the right of delta epsilon, or delta a plus epsilon of t. Because what's going to be happening when you do that is those rectangles that you made are going to be getting skinnier and skinnier as you bring epsilon in this way. But the problem is the rectangles are also going to be getting taller and taller, because remember, the height of this is 1 over epsilon. So as epsilon goes to 0, the rectangles get skinnier, which ends up looking like instantaneous impulse, but then the function runs off to infinity. So the limit doesn't exist as a function in the way that we're used to. But let's just suppose that it existed in some sense. For those of you that are technically minded, the sense in which this is going to exist is the sense of distributions or generalized functions. And that's beyond the scope of the course, but there is a context that's very well developed in which this limit does make sense. So let's just assume that there's some object here that is the limit called delta a of t. What properties does delta a of t have as a limit? Well, it's pretty clear that for every other value of t except for a, this limit is 0, because, you know, this function is going over, going up, popping back down again. As epsilon goes to 0, and this interval gets narrower and narrower, there's fewer and fewer places where this function goes up. So if epsilon went to 0, there's no other value except a where this thing could possibly have a value. So the first property that we get from defining delta as a limit is that delta a of t is equal to 0 whenever t is not equal to a. Now notice I didn't tell you what happens at a. I'm just telling you what happens at not a. The second property comes from integrating delta. The integral from minus infinity to infinity of delta a plus epsilon of t dt is equal to 1 for any value of epsilon. That's always true. That's like a sequence of ones. No matter how small you make epsilon, the integral is still 1. So what we do is we say, okay, well, if the limit of the first step makes sense, if I could take the limits of the delta functions and get some kind of thing out that I call delta a, then the integral of this sequence of things, each entry of which is 1, must also be 1. And so it must be the case that the limit as epsilon goes to 0 of the integral from minus infinity to infinity of delta a plus epsilon of t dt is also 1, because every single one of these integrals was 1. If you got a 1 and 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 1 and you take a limit, the only limit it could possibly have is 1. Now notice, I never actually had to tell you anything about the value of delta at a in order to tell you that its integral is 1. And this is sort of the cheesy trick that you use to get around the fact that delta is not really a function, is the properties we really care about come from the way that we integrate it. And so this object, the limit of these step functions, these rectangles, this is called the Dirac delta function. And those two properties are its key features. So the upshot of what we've just talked about is that delta a plus epsilon of t is a difference of step functions, ua of t minus ua plus epsilon of t over epsilon, which looks like a derivative. We define delta a of t to be equal to the limit as epsilon goes to 0 from the right of delta a plus epsilon of t. That exists in the sense of distributions, which you can learn about in a graduate course. And the two properties that we really care about is that delta a of t is equal to 0 when t is not equal to a, and that the limit as epsilon goes to 0 of the area underneath the delta function is 1. Okay? Now, there are two other really important properties that delta has. The first is that delta does something when you multiply it by a function. And the second is that delta has a Laplace transform. And those are the next things that we're going to talk about. Okay? Now, what is weird about delta is that, again, the way that you visualize delta is an infinitely thin, infinitely tall rectangle that when you integrate it, you produce a 1. That's weird. And that's why it's not really a function. So this is called the delta function, but it would be most appropriate to put function in quotation marks and instead say something like distribution or generalized function. So there's a whole world of these objects running around out there that are really useful. All right, so now we're going to take a look at what delta does when you multiply it by a function f, which is actually pretty interesting. So if I took the integral from minus infinity to infinity of delta a of t f of t dt, I can't just somehow reduce this to an integral from a to a, because that would be assuming that delta was acting like a function, and the result that came out would be a 0. But remember, it's not a 0 because delta in some sense is infinitely tall. So I can't evaluate the integral using the fundamental theorem of calculus because delta is not a function. Instead, what I'm going to do is I'm going to use the same limit trick that I used before. I'm going to think of this as being equal to the limit as epsilon goes to 0 of the integral from minus infinity to infinity of delta a plus epsilon of t times f of t dt. So what does that mean? Well, that's going to give us an integral that looks like a step function, because this is defined in terms of step functions, right? So we're going to get the limit as epsilon goes to 0 of the integral from minus infinity to infinity of 1 over epsilon times ua of t minus ua plus epsilon of t f of t dt. But remember that this switch right here means that f, when we multiply that switch by f, what we're saying is that whole function on the inside, and now it is a function, that whole function on the inside is 0 everywhere except the numbers between a and a plus epsilon. That's what it does. It turns f on just for that little interval. So this turns out to be equal to the limit as epsilon goes to 0 of the integral from a to a plus epsilon of 1 over epsilon times f of t dt. Okay, so if f has an antiderivative, what does this look like? Well, let's see. So the 1 over epsilon does not have anything to do with the integral, so it can pop outside. So now we have a limit as epsilon goes to 0 from the right of 1 over epsilon times the integral from a to a plus epsilon of f of t dt. But this statement is just saying take the antiderivative of f and plug in a plus epsilon and a. 1 over epsilon, integral from a to a plus epsilon of f of t dt. This is just the limit as epsilon goes to 0 of 1 over epsilon times capital F of a plus epsilon minus capital F of a. And that should make you suspicious. This is where f is the antiderivative of little f, right? Because this looks like the following. F of a plus epsilon minus f of a over epsilon, where capital F prime is equal to little f. This thing, that thing right there, that's just an expression for the derivative of capital F. In fact, this is, by definition, this is f prime of a. But what is f prime? F prime is little f. So the delta function, when you stick it inside of an integral, evaluates a function at a. The purpose of this entire calculation is that what we've shown is that if I took the integral from minus infinity to infinity of delta a of t, and I multiply it by f of t dt, what falls out of this integral in the end is just f of a. That's pretty awesome. So delta is not really a function, but it does all this really cool things that no function can do. Okay, so that property is really important. The fact that a delta function reproduces the value of a function at a when you integrate against delta. This is what we mean by when we say a point mass. Delta basically lets you measure how much of a function exists at a single point. Okay, so that's our third property. The integral from minus infinity to infinity of delta a t f of t dt is just f of a. And that property is going to give us our fourth property, which is the Laplace transform. What is the Laplace transform of the delta function? And why would we want it, first of all? Well, delta functions are what's used to impart impulse in a differential equation. Putting a delta function in at point A is a way of contributing. Remember, it's a differential equation, so to solve it implicitly, you're using integrals. So what that's going to do is it's a way of introducing an instantaneous force. If I want an instantaneous contribution of 10 newtons, I could just put a 10 delta on the other side of a differential equation, and that would give me a contribution of 10 units of force at a specific moment. Okay? All right, so what is its Laplace transform? Well, the definition of the Laplace transform says this is supposed to be the integral from 0 to infinity of delta a of t times e to the minus st dt. And this is actually the same as the integral from minus infinity to infinity, because delta is equal to 0 over there anyway for positive values of a. So if I like, I can think of this as being the integral from minus infinity to infinity of delta a t e to the minus st dt, specifically because delta a, this thing is equal to 0 from minus infinity to 0. All right, well, now what? Now, I already know how to do that because I've got an integral where I've got delta times a function f of t. My rule says that when I have an integral of this form, it just evaluates the function. So what is the Laplace transform of delta a of t? It's the value of this integral, which is just e to the minus as. By rule 3, the Laplace transform, which is really this integral, just evaluates that function at a. So it replaces t with a. There's the Laplace transform of the delta function. Well, that's brilliant. Because now we have a tool we can use to solve differential equations with. So that's our fourth property. So our four properties for the delta function are: 1, delta a of t is equal to 0 when t is not equal to a. 2, the integral from minus infinity to infinity of delta a of t dt is equal to 1. The third property is that the integral from minus infinity to infinity of delta a of t f of t dt is just f of a. That's called point evaluation. And 4, the Laplace transform of the delta function is e to the minus as. That's a useful thing. Okay, so let's look at some examples of how it gets used in practice. So the shifting theorems are going to be involved because the fact that the delta function turns in to an exponential means that when you come back the other direction, there's going to be a shift and a unit step function involved in solving equations that involve it. So let's look at this differential equation. And before we do it, let's see if we can understand what's happening. The first thing to notice is that this is a mass spring system. It's a mass spring system because the constants of our equation are all positive. So this represents a simple harmonic oscillator. Now what happens on the right-hand side? The right-hand side is 0 until we get to t is equal to pi. And then all of a sudden there's a shock to the system. That's what the delta function does. At t equals pi, a unit impulse is imparted to the system. And then immediately it's not there anymore because it's a delta function. So that shock is going to do something to the system, and it should be modeled with the solution that we see. All right, so I want to hit this with a Laplace transform, but we don't have the delta written in the delta A form yet. And so the idea is to figure out what is the point at which that delta function has something that's not a 0. And the answer is the number pi, because t minus pi that's sort of where that spike is going to happen. So this is really the function delta pi of t. So delta pi of t is equal to delta of t minus pi. If I don't put a subscript there, it means delta 0. So I'll rewrite the equation into this form. So I hit everything with a Laplace transform, and this is what we're going to get. We're going to get s squared y of s minus 2s minus 1 plus 4 times s y minus 2 plus 13y is equal to e to the minus pi s. All right, multiplying through and pulling out the algebra, we're going to get that s squared minus, not 2s, 4 times sy, so there's a plus 4s, and there's a plus 13, and that makes me comfortable because I see up at the top that this agrees with the characteristic polynomial for the left-hand side. And that's going to be equal to, so there's going to be a 2s and a 9 and an e to the minus pi s on the right-hand side. So now we just continue with our typical Laplace transform mathematics. Oh, I guess it would be helpful if I put the y in there. And that's going to get us that y of s is equal to 2s plus 9 plus e to the minus pi s over s squared plus 4s plus 13. So our standard algebra is going to look like this. Y is going to look like, well, there's going to be an e to the minus pi s, and then completing the square in the denominator is going to get me s plus 2 squared plus 9. And then I'm going to have a 2s over s plus 2, well, I guess I have a 2s plus 9 over s plus 2 squared plus 9. So I'm going to notice there's a shift here, which means that there's an exponential that has been multiplied in the time domain. But in order to recover that exponential, all of the copies of s in this problem have to have the same quantity in the, they have to all include the same shift. Okay. From here, we're going to do our typical shifting theorem operation. And so we're going to rewrite this line as y is equal to e to the minus pi s over s plus 2 squared plus 9. And then in order to get the s plus 2's that we need in to the cosine that I'm really looking at here, I'm going to have to write this as 2 times s plus 2 over s plus 2 squared plus 9. And that grabbed 4 from that 9, and so there's 5 left over to be the sine. And of course, we're going to have to multiply in a 3 and divide out a 3 in order to get that sine there. Okay, so hit this with the inverse Laplace transform. Y of t is equal to the inverse Laplace transform of e to the minus pi s over s plus 2 squared plus 9 plus the inverse Laplace transform of 2 times s plus 2 over s plus 2 squared plus 9 plus 5/3 times the inverse Laplace transform of 3 over s plus 2 squared plus 9. And now I've got shifting theorems to deal with. right? So I have this complex, or I've got this exponential that's got an s in it, and I've got s plus 2's running all over the place. So both shifting theorems are actually going to be used in undoing these Laplace transforms. This one, the s plus 2 corresponds to an e to the minus 2t in the time domain. So this one is easy because you get 5/3 times e to the minus 2t sine of 3t. That's this one. Likewise, this one is easy because if you undo the shift, you're just looking at twice a cosine. So this one is equal to 2e to the minus 2t times the cosine of 3t. So you can think of this part as corresponding to the state of the system prior to the introduction of the shock. Okay? It's sort of the base operation of the system incorporating the initial conditions. This term is going to be the term that introduces the shock to the answer. Okay, so let's deal with the last term. And the way we're going to deal with the last term is we're going to try to slowly unravel what's happening here. So the last term is going to be the Laplace transform of, well, let's see what happens. The e to the minus pi s I'm going to deal with last. I know what the inverse Laplace transform is of 3 over s plus 2 squared plus 9. So I'm going to get a 1/3 times a Laplace transform of e to the minus 2t times the sine of 3t, because that's what turns into that shape up there. Once I get rid of the e to the minus pi s, that's what's in there. In doing that step, I have used the first shifting theorem, but now I'm going to have to use the second shifting theorem because there's this pi involved. And in order to do that, I'm going to have to rewrite the function to incorporate the shift. So the inverse Laplace transform of something that looks like this by the second shifting theorem is the following. 1/3 times a shift of pi times e to the minus 2 times t minus pi sine of 3 times t minus pi plus the part that was already here. 2e to the minus 2t cosine of 3t plus 5/3 e to the minus 2t sine of 3t. This is the solution to the equation. And it has the exact behavior that we'd expect to happen. If we just ignore this term for a second, put my hand up over the top of it. If we ignore this term for a second, this part of the equation acts exactly like we think it should. We have a problem where we've got oscillating behavior, but the oscillating behavior is decaying to 0 because this e to the minus 2t is collapsing the system to 0. That's what happens when you have a damped oscillator. You let the spring go, or the mass go, and the spring drives it, but the damp makes it settle into 0. On the other hand, we have this other term that doesn't start being active until we get to t is equal to pi. That's what this unit step function does. It turns this function on. And what does it do when it gets there? It introduces a new oscillatory force to the system. And we still have exponential decay because the force was just instantaneous. There's no forcing function. Instantaneously, this force was delivered, and then the system starts again exponentially decaying to the origin. So the behavior that we see in the solution is precisely what we expect. The base behavior of the system, the intrinsic behavior of the system, and then a term that only turns on when we get to t equals pi that models what happens once the impulse hits. Okay? So I can pull up a quick graph of this and you can see what it looks like. So this is what the plot of this equation actually looks like when you stick it into any plotting program. I've used x as my variable here instead of t, but you can see from the graph that what we're looking at here is the initial behavior of the system, this damped oscillator, is to come down from 2, and then the damper sort of comes back over the line. That means we know that this is underdamped, right? That we're getting this sort of behavior. But then it settles in, and then we don't actually know what happens past this point because at pi, that is at 3.14, now the impulse hits the system and pushes it back up again. Now why up? Because the impulse was positive, right? +1 in this case. And so that's going to drive the mass in the positive direction, which pushes it back up again. And then again, we see the exponential decay back to the axis. And the idea here is that this is the shock in the system. It happens right there at t is equal to pi. And that is precisely what we expected to happen when we set up the original equation that looked like, let me find the slide. This. because in this equation, we had some sort of base initial condition where I've pulled the mass up to height 2, and then I've imparted some upward velocity to it. But the damp is going to pull it back to the origin until I get to t equals pi, and that's where the shock happens. Okay? And again, I want you to connect what we are looking at the equation here, the intuition that we've drawn from that equation about what the answer should look like, and what the answer actually does look like when you plot it, which is there's the shock to the system. So you can view this kind of function, the utility of this kind of function is in modeling those kind of shocks to systems. And again, those shocks can correspond to things like flipping a switch or hitting a bump or a sharp strike or a collision. Okay, so that is what the delta function is and what it does. It's incredibly useful. It turns out that it deeply is tied to the shifting theorems because the answers have to come from somewhere, right? How are you going to have a function that turns on after a shock happens? Well, automatically that's going to correspond to a shift and a unit step function. So it's very typical in these problems to get behavior like this, where you have a delta function hits a differential equation at some point, and then in the answer, you get a unit step function that turns on a piece of the answer that applies after that shock has happened. So the last thing I want to talk about is the convolution theorem. And the convolution theorem for the Laplace transforms actually turns out to be identical to the convolution theorem for Fourier transforms. So the fact that the convolution theorem holds is going to be what allows us to use the Laplace transform in a lot of really interesting ways to change the way that systems behave. So like in control theory, for example, the convolution theorem is really important because it lets you do stuff in the Laplace domain and then transform it back into the time domain in an understandable way. The convolution theorem for Laplace transforms looks like this. First, I guess to remind you what a convolution is. So in the context that we're talking about, because we are convolving not from minus infinity to infinity, like in the Fourier domain, but from 0 to infinity, in the Laplace domain, so a Laplace convolution is not defined from minus infinity to t, it's defined from 0 to t. So f convolved with g of t is equal to the integral from 0 to t of f of t minus x g of x dx. There's a convolution. It's identical to the Fourier context, except we're only working on the right half line, the positive numbers. And convolutions have a lot of properties that make them act like multiplication. We can point out again to remind you that it's symmetric. The convolution of f with g is the same as the convolution of g with f, that it is associative. The convolution of f with g convolved with h is f convolved with g convolved with h. That's very multiplication-like. And the fact that we can distribute it, that f convolved with g plus h is equal to f convolved with g plus f convolved with h. So the upshot of all of this is convolution is very much like a multiplication. Convolution acts like multiplication. Okay? And that's basically the role that it plays. It's the special sort of multiplication that comes out from rearranging integral formulas. So the convolution theorem for Laplace functions says the Laplace transform of f convolved with g is the Laplace transform of f multiplied by the Laplace transform of g. Or more typically, f of s, g of s. And then since every Laplace transform formula comes with an inverse formula, it's also the case that the inverse Laplace transform of a product is a convolution. So I'm not just like throwing a theorem at you without telling you how to use it. I'm going to do a couple of quick examples of how the convolution theorem works in this context. So you might look at something like the inverse Laplace transform of 1 over s squared times s minus 1. This is an example from the textbook. Previously, what we would have done is use partial fractions to pull that apart, but you can actually look at this as the inverse Laplace transform of 1 over s squared times 1 over s minus 1, and multiplication in one domain corresponds to convolution in the other. What the convolution theorem says is that this is equal to the inverse Laplace transform of 1 over s squared convolved with the inverse Laplace transform of 1 over s minus 1. Since the inverse Laplace transform of 1 over s squared is the function t, and the inverse Laplace transform of the function 1 over s minus 1 is e to the t, so this is actually a t, and this is an e to the t. If you wrote down the definition of the convolution, what you get is the integral from 0 to t of t minus x times e to the t, e to the x dx. And that would be one way, you could actually evaluate this using integration by parts, and it will give you the same answer that you would get doing partial fractions. Okay, it's not always clear that this integral is going to be solvable. And in fact, in many cases, the partial fraction step in an inverse Laplace transform is so hard that you'd rather just have an integral that you could look at and stick into a machine to evaluate than try to write it down as a bunch of individual pieces. Okay, so if you want to look at how the solution to this is done, you can just integrate it by parts. Another place where we use the Laplace transform is when we're solving equations generically, and we want formulas that express the answers to an equation, but we don't have anything specific to refer to. So a good example of this is actually presented in the text as example 10.9.7, and that says, consider the equation y prime prime plus omega squared y is equal to some generic forcing function f of t. So omega is some constant we don't know. And also I tell you the initial conditions are constants that we don't know. Y of 0 is alpha and y prime of 0 is beta. So everything in this equation is generic. How can I write down a solution that describes this for all possible answers, for all choices of parameters a, b, and omega? Well, I can use the Laplace transform to do it. So if I Laplace transform this, which is completely legitimate to do, I'm going to get s squared y minus alpha s minus beta plus omega squared capital Y is equal to capital F of s. And that's going to tell me that I'm going to get, after I factor everything out, I think I get s squared plus omega squared y is equal to alpha s plus beta plus f of s. And so y is equal to alpha s plus beta over s squared plus omega squared plus f of s. I can break that up into pieces to get that this is alpha s over s squared plus omega squared plus beta over s squared plus omega squared plus f of s over s squared plus omega squared. Again, everything is fully generic at this point. I haven't added any sort of... I'm tracking this equation at its full level of generality. And this is a solution to this generic equation in the Laplace domain. How could I write down what its time domain solution is? If I start with y is equal to alpha s over s squared plus omega squared and beta over s squared plus omega squared, and instead of thinking about it as f of s divided by s squared plus omega squared, instead I'm going to think about it as f of s times 1 over s squared plus omega squared. Now I can translate everything back into the time domain, except for this, which I'll have to write down using a convolution, because this is a product of Laplace transforms. So when I come back the other direction, this is going to turn out to be an alpha cosine of omega t, and then I'm going to get a beta over omega sine of omega t. And then this last term, I have to use an integral to define because it's going to be a convolution. This is going to be equal to the integral from 0 to t of little f of t minus x times 1 over omega times the sine of omega x dx. And that's the best I can do in that equation. I can't do any better than that. But the basic idea is that whatever f is, I have completely written down the solution to this totally generic equation, y prime prime plus omega squared is equal to capital, or like f of t where y of 0 was alpha and y prime of 0 is equal to beta, by using the convolution theorem, I have written down a completely generic solution to this for any values of alpha, beta, and omega you choose. I have completely described this solution. And there's a lot of power in describing entire families of functions with one solution that depends only on the choice of parameters. So you should think this is the place where the study of this kind of mathematics goes from thinking about individual equations to giant families of related systems. And so we're not studying a single equation, we're studying a family of equations that can all be generated from the same skeleton, but then have a unified structure for their solutions. And in practice, usually what you do when you've got an equation like that is you've got some freedom to wiggle the parameters around to make sure that the solution acts in a way that you find acceptable in whatever context you're working in. All right, so with that heavy blast of convolution theory, we are finished with the content of the course. I will tell you that I have been thrilled to teach this class for you guys. You've worked very hard. This has been enormously fun for me to do. I'm appreciative of the work that you've put in, and I hope to see you in the future. Maybe you can tell me about how this stuff came up in the classes that you're taking or the classes that you are taking in the future. I think that linear analysis is the core of pretty much the entire modern understanding of the way that mathematics and the sciences intersect with each other. And they have applications in surprising areas from computer science, biomechanics, biomedicine, engineering, applied mathematics, pure mathematics. It's an incredibly important set of ideas. It's been an absolute privilege to walk you guys through it. So good luck, and I will talk to you going forward. Take care.